A supernova is already one of the most violent events in the universe. A star dies, its core collapses, its outer layers explode into space, and for a brief time, one dying star can shine brighter than billions of suns. But sometimes, a supernova is not enough. Sometimes a star is so massive, so unstable, and so extreme that its death becomes something even more powerful. A hypernova. Not just an explosion, a cosmic detonation, a final collapse so violent that it can release more energy than an ordinary supernova, tear a massive star apart, forge heavy elements, and sometimes launch beams of radiation across space at nearly the speed of light. If one of those beams is pointed toward us, we may see it as a gamma-ray burst, one of the brightest flashes in the known universe. But what would a hypernova actually look like? Not from a telescope image, not as a graph, but as an experience. Imagine standing impossibly far away, safe in deep space, watching a massive star reach the end of its life. At first, it looks almost calm, a giant star glowing in silence. But deep inside, the core is already collapsing. Gravity is winning. The star's heart is becoming a neutron star, or falling even deeper into a black hole. Then the surface breaks. A blinding flash erupts. Twin jets tear through the star. A shockwave rips its layers apart, and the darkness around it is suddenly filled with light, fire, radiation, and the raw material of future worlds. Before we begin, if you enjoy calm, cinematic space documentaries made for sleep, mystery, and deep cosmic questions, make sure to subscribe to Theories Before Sleep. Tonight, we are not watching a normal star die. We are witnessing one of the most extreme deaths in the universe, a hypernova, the kind of explosion that can light up galaxies and leave behind darkness. A nova, a supernova, and a hypernova all sound like different names for the same thing. A star brightens, a star explodes, a new light appears in the sky. But they are not the same. A nova is the smallest of the three. It usually happens in a binary star system, where a white dwarf steals gas from a companion star. That stolen material builds up on the white dwarf's surface until it ignites in a sudden burst of nuclear fire. The star becomes dramatically brighter, then fades again. But the white dwarf survives. A nova is violent, but it is not the death of the star. A supernova is different. A supernova is the death of a star, or the destruction of a white dwarf. It can happen when a massive star runs out of fuel, collapses under gravity, and blasts its outer layers into space. Or it can happen when a white dwarf gains too much mass and tears itself apart. A supernova can outshine an entire galaxy. It can forge elements. It can leave behind a neutron star or a black hole. It is one of the most powerful explosions in the universe. But then there is something beyond it, a hypernova. A hypernova is not just a bigger supernova in a simple way. It is the death of an extreme star, a star so massive, so energetic, so unstable, and so violent that its final collapse releases far more energy than an ordinary supernova. This is the most powerful kind of stellar explosion we know. Not a small star dying, not a sun-like star fading into a white dwarf, not even a normal massive star exploding. A hypernova belongs to the rarest monsters in the universe. Only the most massive stars can create one. A star perhaps 30 times the mass of our sun or more. A star that lived fast, burned hot, and spent its fuel with terrifying speed. These stars do not live for billions of years like our Sun. They may live only a few million years. They are born as giants. They shine with incredible brightness. Their stellar winds tear material from their surfaces. Their cores burn through elements faster and faster. Hydrogen, helium, carbon, oxygen, silicon, until finally the core reaches the point where fusion can no longer save it. Then gravity takes over, and for a normal massive star, this can already produce a supernova. But in a hypernova, the collapse is more extreme. The star may be rotating rapidly. Its core may collapse directly into a black hole. Material may fall inward with enormous force, forming an accretion disk around the newborn black hole. Magnetic fields twist, energy builds, and sometimes narrow jets of radiation and matter blast out from the poles of the dying star at nearly the speed of light. If one of those jets is aimed toward Earth, we may detect it as a gamma-ray burst, one of the brightest flashes in the universe, a signal so powerful that for a few seconds it can be seen across billions of light-years of space. This is why hypernovas feel almost unreal, because they are not only explosions, they are engines. A massive star collapses. A black hole may form. Jets tear through the star. The outer layers detonate outward. Heavy elements are scattered into space, and the universe receives one of its most violent messages. Light, radiation, shockwaves, matter, all from the final seconds of one dying star. Their energy scale is almost impossible to imagine. In only seconds, a hypernova can release more energy than our Sun will produce over its entire lifetime. Our Sun will shine steadily for around 10 billion years. It will warm planets. It will hold the solar system together. It will spend its energy slowly across deep time. A hypernova releases a comparable cosmic violence almost instantly, not carefully, not gently, all at once. A dying star spends its last breath like a universe-sized explosion. For a long time, astronomers did not clearly separate hypernovas from supernovas. They saw stars explode. They measured their light. They studied the spectra. But then some explosions appeared too energetic, too broad, too extreme to fit the usual categories. One of the most famous turning points came in 1998, with the explosion known as SN 1998 BNW. It was connected with a gamma-ray burst, GRB 980425, and it became one of the key events that helped astronomers understand that some supernovas were far more energetic than ordinary ones. This was the moment the universe showed us that supernovas had a more violent cousin. Not every gamma-ray burst comes from the exact same kind of event. Not every hypernova points its jet toward us. But the connection between some hypernovas and long gamma-ray bursts opened a new chapter in astronomy. It meant that when we detected a flash of gamma rays from deep space, we might be seeing the death of a massive star across the universe, a star collapsing into darkness, a black hole being born, a jet escaping through the star's body, a hypernova lighting up the cosmos. And yet, they are incredibly rare. Most stars are too small. Red dwarfs will never explode this way. Sun-like stars will never explode this way. Even many massive stars will only become ordinary supernovas. To create a hypernova, the star must be extreme from the beginning. Very massive, fast burning, often stripped of much of its outer hydrogen, possibly rotating fast enough to help power the central engine. Everything has to be pushed toward the edge. That is why a galaxy like the Milky Way may only produce something like this on very long timescales, perhaps once in hundreds of thousands or millions of years. We have never seen one happen up close in our own time. And that is probably good, because a nearby hypernova would not simply be a beautiful event in the sky. It could be dangerous if the explosion were close enough, and especially if one of its jets were pointed toward Earth. The radiation could damage atmospheres, disrupt chemistry, and threaten life across planetary surfaces. A hypernova is beautiful from a safe distance, but close up, it is not beauty. It is extinction-level violence. That is why tonight, we do something impossible. We choose a safe distance, far enough to survive, close enough to see. Our observation platform waits in deep space, protected by advanced shields, watching a massive star that has already reached the end of its life. From the outside, it still looks like a star. Huge, bright, ancient, maybe blue-white, maybe stripped and unstable, maybe surrounded by shells of gas it threw off in its final centuries. It looks alive, but inside, the core is already doomed. The fuel is gone. The final elements have formed. The balance has failed. Gravity is preparing to win. And when it does, the star will not die quietly. It will collapse. It will break. It may give birth to a black hole. It may launch jets through its own body. It may create a blast so bright that distant galaxies could see it. A hypernova is one of the most violent events the universe can produce through the death of a star. It is not only the end of a giant, it is the moment a star becomes a cosmic weapon, the moment gravity turns light into catastrophe, the moment death becomes bright enough to cross the universe. Tonight, we are going to watch it happen. From the first signs of instability, to the collapse of the core, to the eruption of the jets, to the explosion that tears the star apart, to the black hole or neutron star left behind in the dark. We are not watching a normal stellar death. We are watching a hypernova, the rarest kind of stellar ending, the universe's most extreme goodbye. And somewhere inside that enormous star, the final countdown has already begun. We arrive far from the star, 100 light years away, far enough that the star is only a brilliant point to the naked eye, but close enough that our instruments can see the violence already beginning around it. Our observation platform drifts in silence, suspended in deep space, shields active, telescopes awake, every detector pointed toward the same distant light. At first glance, the star looks beautiful, blue-white, brilliant, almost pure. But this is not an ordinary star. This is a Wolf-Rayet star, one of the most extreme stars known to science, a star so hot, so massive, and so unstable that it already looks like something close to death. Wolf-Rayet stars are rare. They are the stripped cores of massive stars, stars that have lost much of their outer hydrogen layer and now expose deeper, hotter material beneath. Their surfaces are not gentle. Their light is not calm. Their winds are not soft. They are stellar giants being torn apart by their own power. The star in front of us has about 40 times the mass of our sun. 40 suns gathered into one object. But it does not shine like 40 suns. It shines like a million. Its luminosity is almost impossible to imagine. Every second, it releases energy at a rate our sun could never approach. Around it, space is flooded with radiation. The The surrounding gas glows under the pressure of its light. Dust is pushed away. Nearby material is carved into shells and arcs. Its surface temperature may reach around 50,000 degrees, nearly 9 times hotter than the surface of our Sun. That heat gives it a fierce blue-white color, the color of a star burning at the edge of physics. From Earth, a star like this might look like a bright point in a telescope. From our position, it feels alive with violence. The star is not simply shining, it is losing itself. Powerful stellar winds blast from its surface at incredible speeds, carrying material into space. Every moment, the star throws away part of its own body. Gas streams outward, layers are stripped away. The outer atmosphere is no longer stable enough to remain bound. A normal star has a solar wind. This star has a storm, a continuous outflow of charged particles, radiation, and hot gas strong enough to sculpt the space around it. The wind has created a nebula, not a peaceful nebula like the soft remains of a sun-like star, but a turbulent shell of material blown outward by a star that is too bright for its own surface to hold together. Around the Wolf-Rayet star, the nebula glows in broken shapes, curving arcs, shocked gas, fragments of old material pushed outward, thin filaments lit by ultraviolet radiation. The star has already begun writing its ending into space. Before the hypernova comes, the system is already marked by violence. From our observation platform, the star flickers slightly. Not because it is weak, because it is unstable. Its outer layers pulse, its brightness shifts. Its surface seems to breathe in waves of pressure and heat. Giant regions of plasma rise and fall. Magnetic fields twist through the stellar wind. The star sheds mass unevenly, as if it is trying to tear itself open before the final collapse. But the real catastrophe is not on the surface. It is deep inside, far beneath the blue-white glare, beneath the exposed layers, beneath the wind, beneath the violent outer shell. The core is entering its final state. For millions of years, this star has burned through fuel with terrifying speed. Hydrogen first, then helium, then carbon, then neon, then oxygen, then silicon, each stage shorter than the one before it. The star has lived fast because it was massive. Its gravity crushed the core to extreme temperatures. Its fusion reactions burned furiously. Its light was magnificent because its life was being spent quickly. Now, at the center, the last great mistake is forming: iron. Iron is different from the elements that came before it. When lighter elements fuse, they release energy. That energy creates pressure. That pressure helps hold the star against gravity. For millions of years, fusion has been the star's defense. But iron does not save a star. Iron is the end. Fusing iron does not release useful energy. It takes energy away. So when iron begins to collect in the core, the star is no longer building fuel. It is building a dead center, a poison element, a core that cannot burn its way out of collapse. Every second, the iron core grows heavier. Layer by layer, the star's final burning stages add more mass to the center. Around the core, shells of fusion continue for a short time, but they are no longer a solution. They are only delaying the inevitable. The star is like a cathedral with its foundation crumbling in darkness. From outside, the walls still stand. The windows still glow. The shape still seems whole. But deep below, the support is failing. Our instruments detect what our eyes cannot. The star still looks normal in visible light, at least normal for something so extreme. It is bright. It is hot. It is surrounded by a wind-blown nebula. It pulses. But Wolf-Rayet stars are known for instability. Nothing in the ordinary image would tell a distant observer that the final collapse is close. But the observatory is not watching only invisible light. It is listening to the core. The neutrino detectors begin to notice a slight change, a faint increase, not the enormous flood that will arrive during collapse. Not yet, but a warning. Deep inside the star, nuclear reactions are entering their final stages. The core is becoming hotter, denser, more desperate. Neutrinos begin escaping from regions no light can reach. They pass through the star as if the star is almost transparent. Light is trapped. Neutrinos are not. They come first. They tell us the truth before the star does. The platform systems mark the change. The signal is small but real. The star's interior is no longer in ordinary late life. It is preparing to break. We adjust the instruments. Gamma-ray detectors are armed. X-ray telescopes focus. Radio antennas listen. Spectrometers begin continuous scans. High-speed cameras prepare for the first visible shock. The observatory shifts slightly, keeping its angle away from the star's poles. If jets form during the collapse, we do not want to be directly in their path. From 100 light-years away, a hypernova is spectacular, but a jet aimed straight at us would be something else entirely. This is the danger of a hypernova. The explosion is not always perfectly spherical. In the most extreme cases, the core collapse can launch narrow beams from the poles of the star. Those beams can carry incredible energy through space. If one points toward a distant world, that world may see a gamma-ray burst, a flash so bright it can cross billions of light-years, a cosmic signal from the death of a giant. Tonight, we are watching from the side, safe enough to survive, close enough to witness. The Wolf-Rayet star continues to shine. Its nebula glows around it like a warning halo. The stellar wind rips outward, carrying material away at tremendous speed. Gas piles into shells. Shock fronts ripple through the surrounding cloud. The star seems to be surrounded by its own storm system, larger than any solar system, moving through space in silence. And yet, for all its violence, the most frightening thing is how normal it still looks. There is no final alarm in the visible surface, no countdown written in light, no crack splitting the star open, just a bright, unstable, beautiful star, already doomed from within. The iron core is approaching the point of no return. Soon, it will grow too massive to support itself. Electron pressure will fail. Gravity will take over completely. Matter will collapse inward at a significant fraction of the speed of light. Protons and electrons will merge into neutrons. Neutrinos will flood outward. The core will become either a neutron star or, if the mass is too great, fall straight toward a black hole. And because this is not an ordinary massive star, because this is a stripped, extreme, rapidly dying giant, the collapse may create something more than a supernova. It may create a central engine, a newborn black hole surrounded by infalling material, an accretion disk hotter than almost anything in the universe. Magnetic fields twisted into violent order. Jets drilling outward through the star. A hypernova beginning from the inside. The thought is almost impossible to hold. The star before us is huge enough to dominate its region of space, bright enough to outshine millions of ordinary stars, hot enough to glow blue-white, powerful enough to sculpt a nebula around itself. And still, it is fragile, because all of that power depends on balance, gravity inward, energy outward, and at the core, that balance is ending. The neutrino flux rises again, slightly, quietly. The instruments confirm it. Something is changing deep inside the star. The first warning has arrived. From the outside, the Wolf-Rayet star is still shining, still beautiful, still enormous. But now we know the truth. The star is no longer only dying. It is entering its final moments. A catastrophe is building beneath the surface. Iron is gathering at the center. Gravity is waiting. And somewhere inside that blue-white giant, something is about to break. The final day begins almost quietly, not peacefully, not safely, but quietly in the way space is always quiet. No sound reaches our observation platform. No roar, no warning siren from the star, no thunder rolling through the vacuum. Only light, only radiation, only data. 100 light-years away, the Wolf-Rayet star still burns in front of us, blue-white and furious, wrapped in its own wind-blown nebula. It has already spent its life too quickly. It has burned hotter than the sun, brighter than the sun, faster than the sun. And now it has less than 24 hours left. From the outside, it is still beautiful. A massive stellar body surrounded by glowing gas, a bright core inside a shell of material it has already thrown into space. But the instruments show that something has changed. The star is no longer pulsing gently. It is convulsing. Its brightness rises and falls in uneven patterns. Not the clean rhythm of a stable variable star. Not the slow breathing of an aging giant. This is irregular, violent, broken. The surface brightens suddenly, then dims. Regions of plasma swell outward. Hot gas erupts from the surface and is thrown into space. The stellar wind intensifies, becoming faster, denser, more chaotic. The star is shedding mass as if it can no longer hold itself together. Every hour, more material escapes. Every hour, the surrounding nebula becomes thicker. Around the star, a fresh shell of gas begins expanding outward. It is not the hypernova yet, not the final explosion, but it is the star tearing pieces of itself away before the end. A warning halo, a last breath before collapse. Our telescopes follow the shell as it spreads. The gas is hot, bright, and unstable. It glows under the ultraviolet radiation of the star, forming arcs and knots around the dying giant. Some of it moves faster than other parts, making the shell uneven, broken, almost wounded. The star has become a storm around itself. And still, the catastrophe that matters most is hidden deep inside. The neutrino detectors continue to rise. At first, it was only a subtle increase, a whisper from the core. Now the signal is clearer. Something inside the star is accelerating. Nuclear reactions are entering their final moments. The core is hotter than it has ever been before. In a star like this, the final fuel is silicon. That is the last stage. Hydrogen was the long childhood. Helium was the next chapter. Carbon, neon, and oxygen burned more quickly. But silicon burning is the final countdown. Inside the core, silicon is being fused into iron group elements. This is the last nuclear reaction that can support the star in any meaningful way. It is the last source of pressure before gravity takes everything. And it does not last long. After millions of years of life, the final stage can pass in a matter of days. By the time we are watching now, only hours remain. Silicon continues burning in the core, but it is no longer saving the star. It is building the thing that will kill it. Iron. Every moment, more iron accumulates at the center. The iron core grows heavier, denser, more unstable. The star has spent its life turning lighter elements into heavier ones, each stage releasing energy and holding collapse away. But iron is different. Iron does not give the star energy through fusion. Iron marks the end of the road. A star cannot burn iron to survive. It can only carry it until it becomes too heavy. The instruments build a picture of the hidden center. The iron core is approaching the Chandrasekhar limit, about 1.4 times the mass of the Sun. That is the point where electron pressure can no longer support the weight. After that, there is no pause, no recovery, no second chance. Gravity wins. The countdown has reached its final moments. But outside, the star does not know. That is the terrifying part. The outer layers are still burning, still glowing, still radiating into space. The surface is still sending light outward, and that light still carries the image of a star that appears alive. But deep inside, the core is already beyond rescue. The center and the surface are no longer living in the same story. The surface is hours behind the truth. The core is preparing to collapse. The outer layers still shine as if the star has time. From our platform, we watch that last light leave the star's surface. It travels outward into space, crossing the distance between the dying giant and the observatory. The light we receive is delayed by distance, but the sequence is clear. We are seeing the final hours as they unfold in the star's own history. The final visible calm before the surface realizes what the core has done. The star before us is still whole, but only on the outside. Inside, it is already becoming something else. The pulsations grow stronger. Huge waves move through the outer layers. The star's surface expands and contracts unevenly, like a heart losing rhythm. Bright regions flare across the surface. Darker regions appear where cooler gas rises and falls. Plasma arcs twist into space before being ripped away by the wind. The nebula around the star becomes brighter as new material slams into older shells. The star has spent its final years throwing off gas. Now the newest eruptions crash into those older layers, compressing them, heating them, lighting them up. The space around the star is no longer empty. It is filled with the star's own discarded body. And when the hypernova arrives, all of that material will matter. The blast will strike it. The shockwave will tear through it. The explosion will become even brighter as it collides with what the star lost before death. The star has built the stage for its own destruction. Our platform rotates slightly, maintaining its safe angle. The polar regions of the star are watched carefully. If jets form during collapse, they may escape along the rotation axis. We do not want to be in their direct path. Every detector is now awake. Gamma-ray sensors, X-ray telescopes, ultraviolet cameras, optical systems, infrared imagers, radio antennas, spectrometers, neutrino detectors. The observatory waits like a silent witness at the edge of disaster. The neutrino count rises again. The core temperature climbs. Silicon burning is nearly finished. The iron core is now almost complete. Deep inside the star, the final balance becomes thinner and thinner. Gravity presses inward with impossible force. The core resists for a little longer, supported by quantum pressure, but that support is not infinite. The star has reached the last invisible line. From the outside, it still looks like a star. From the inside, it is already a collapsing future. And then the strangest feeling comes over the observation platform. We are watching something that may already be dead. The visible surface has not yet broken. The final flash has not arrived. The blue-white star still hangs in the dark, pulsing, shedding gas, shining with savage beauty. But the data tells us the truth. The core has reached the edge. The neutrino signal is no longer just a warning. It is the beginning of the end. Somewhere beneath the surface, the last silicon fuel is disappearing. The iron core has grown too massive. The internal support is failing. The collapse has either begun or is about to begin within moments. But we cannot see it yet. The light from the core cannot escape directly. The outer layers still hide the disaster. The star's surface continues sending out its final normal light, unaware that the center beneath it is falling inward. This is what makes the final hours so haunting. The star dies from the inside first. The universe outside only learns later. There is a delay between truth and appearance, a delay between death and light, a delay between collapse and the moment the sky changes. We wait. The instruments record every particle, every flicker, every spectral shift. The star pulses one more time. A huge plume of plasma erupts from one side and stretches into space before being torn apart by the wind. The surrounding shell glows brighter. The neutrino count climbs again. The final light before collapse spreads outward. And then, for a moment, there is an impossible stillness. Not because the star has calmed, because the final threshold has been crossed. Deep inside, the iron core can no longer support itself. Gravity takes hold. The center begins to fall. The collapse starts. The hypernova has already begun. But from our observation point, the star still looks whole. The light has not told us yet. The surface has not broken yet. The jets have not emerged yet. The explosion has not reached the outside. We are watching the last image of the star before the universe reveals what has happened. A beautiful blue-white giant, wrapped in glowing gas, pulsing in its final hours, already dead in its heart. And soon, the light will arrive. The collapse begins where no light can escape. Deep inside the star, far beneath the blazing surface, beneath the violent winds, beneath the glowing shells of gas surrounding it, the iron core finally reaches the point of no return. For millions of years, the star fought gravity with fire. Now, there is no fire left that can save it. The iron core has become too heavy, too dense, too unstable, and then, in less than a heartbeat, it falls. The collapse is almost impossible to imagine. A core roughly the size of Earth is crushed down to the size of a city in a fraction of a second. Something that once stretched across thousands of kilometers is squeezed into a region only tens of kilometers wide. Matter is forced inward with terrifying speed. The density rises beyond anything ordinary matter can survive. Atoms are destroyed. The space inside atoms disappears. Electrons are driven into protons. Protons and electrons merge together, creating neutrons. The heart of the star is no longer normal matter. It is becoming neutron dense. A newborn compact object forms at the center. In an ordinary core collapse supernova, This may become a neutron star, a city-sized remnant with more mass than the Sun, held up by the strange pressure of neutron matter. But in a hypernova, the conditions are more extreme. The star is massive, the core is enormous, the rotation is violent, the magnetic fields are twisted beyond recognition, and the collapse does not simply create a quiet neutron star. It creates an engine. The material falling inward slams toward the newborn core at a significant fraction of the speed of light. Some of it crashes into the compressed center. Some rebounds. Some keeps falling. The inward motion becomes so violent that a shockwave is born. For a normal supernova, this shockwave is already one of the most powerful events in the universe. It begins deep inside the star and tries to push outward, tearing through the layers above it. But even then, the shockwave can struggle. It can stall inside the star, losing energy as it fights through dense material. But this time, something different is happening. The core is spinning too fast. The star did not collapse as a calm, non-rotating sphere. Its center carried angular momentum into death. As the core shrinks, the rotation accelerates, just as a spinning skater turns faster when pulling their arms inward. Only here, the scale is monstrous. The newborn object may spin hundreds of times per second, possibly close to 1,000 times per second. A millisecond engine, a stellar core rotating so fast that its magnetic field is twisted into a cosmic weapon. If the core becomes a magnetar, then it is not just a neutron star. It is a neutron star with an extreme magnetic field, a magnetic field trillions of times stronger than Earth's, maybe even more. Magnetic field lines wrap around the newborn core, stretched, twisted, and amplified by the rapid rotation. The star's center becomes a dynamo of unimaginable power. A spinning magnetar is born inside the collapsing star, and it begins pumping energy into the explosion. This is the trigger that changes everything. A standard supernova is already violent, but a hypernova has an engine at its center. The magnetar's rotation acts like a hidden battery. It stores an enormous amount of energy in its spin as the magnetic field interacts with the surrounding material. That rotational energy is transferred outward into the collapsing star. The shockwave is no longer powered only by the rebound of the core. It is being fed, driven, accelerated. The dying star is being torn apart from the inside by a newborn object only the size of a city, small enough to fit inside a human country, powerful enough to destroy a star, many times larger than the Sun. From the outside, the star has not changed yet. At our observation platform, 100 light-years away, the visible surface is still intact. The blue-white light we see is still the last normal light from the star's outer layers. It still looks like a star, but inside, the star is no longer one thing. It is a battlefield. The core has collapsed. The magnetar is spinning. The shockwave is rising. The outer layers are beginning to lose their support. The explosion is being born. The instruments detect the first true signature, neutrinos, a flood of them. They escape from the collapsing core before ordinary light can. They pass through the star's body almost untouched, crossing the dense layers as if the star were made of mist. To our detectors, the neutrino burst is the first announcement. The core is gone. The collapse has happened. The hypernova has begun. But still, we see no flash. Not yet. The explosion has not reached the surface. The star is so enormous that the shockwave must fight its way outward through layer after layer of stellar material. Silicon, oxygen, carbon, helium, the remains of hydrogen, if any, are left. Every layer the star created across its short, violent life now becomes fuel for the catastrophe. The magnetar continues spinning at the center. Each rotation transfers more energy. The magnetic field becomes a channel. A structure begins to form along the rotation axis. The explosion is not perfectly round. It becomes directional, focused. The star begins to produce jets. Two narrow streams of plasma and radiation form at opposite poles of the collapsing core. They are not gentle beams of light. They are spears of matter and energy, driven by rotation, magnetic fields, and the violence of collapse. They push outward through the star. At first, they are buried. The jets must drill through an entire stellar body. They are born in darkness, trapped inside layers of superheated matter. They tear through the star from within, moving close to the speed of light. The material around them resists. The star is dense, huge, chaotic, but the jets are relentless. They carve tunnels through the dying star's body. Behind them, energy piles up. Shock fronts form. Plasma is heated to extreme temperatures. Matter is accelerated to velocities that feel almost impossible. These jets are what may become the gamma-ray burst. If they escape the star, and if one is pointed toward an observer, a gamma-ray burst is not the whole explosion. It is the narrow, focused scream of the engine inside, a beam so powerful that it can be detected across billions of light years, a flash so bright that, for a few seconds, it can outshine nearly everything else in the gamma-ray sky. From our safe observation angle, we are not directly in the path. That is the only reason we can survive. If one of those jets were aimed straight at us from close range, the event would not be a beautiful spectacle. It would be a cosmic disaster. But from the side, protected by distance, we can watch the birth of the beam. The star's core is now a place of impossible forces. Gravity has crushed matter to nuclear density. Rotation is feeding the central engine. Magnetic fields are twisting energy into direction. The shock wave is growing stronger. The jets are rising. The star is being destroyed from the inside before its surface even knows. This is one of the strangest truths of stellar death. The core can already be dead while the surface still shines. The center can already be collapsing into a magnetar or black hole, while the outer layers continue glowing with old light. The outside of the star is always the last to learn. Our instruments continue recording. The neutrino signal remains intense. The gamma-ray detectors wait for the jet breakout. X-ray sensors watch for the first high-energy leakage. Optical telescopes remain fixed on the surface, where nothing dramatic has yet appeared. But the star's interior is now moving faster than thought. The shockwave accelerates. The jet heads approach the outer layers. The star's outer shell begins to deform. Pressure from below starts to lift the surface. Soon, the star will not be able to hide what has happened. The explosion is climbing upward. The jets are almost free. And when they break through, the hypernova will announce itself to the universe, first as gamma rays, then as X-rays, then as ultraviolet and visible light, then as a growing blast wave that will tear the entire star apart. But right now, in this suspended moment, the event is still hidden. A star appears whole, A surface still burns. A blue-white giant still shines in the darkness. And deep inside it, a spinning magnetar is turning a dying core into one of the most violent engines nature can create. The collapse took less than a second. The trigger has fired. The jets are forming. The shockwave is rising. And the star that once looked eternal is now only moments away from breaking open. From our observation platform, we wait in silence. The instruments are alive. The data is screaming. The light has not arrived yet. But the truth is already clear. The hypernova has begun inside the star. And now its death is racing toward the surface. The jets reach the surface. For a moment, nothing about the star looks like it should survive what is happening inside it. The core has collapsed. A newborn magnetar, or perhaps the first moments of a black hole, is hidden at the center. The shockwave is moving outward, but the jets are faster. Two narrow beams of energy and plasma have been drilling through the star from within, carving tunnels through layers of dying stellar material. They began deep in the collapsed core, trapped beneath the star's outer body, moving through heat, pressure, and density beyond anything ordinary matter should endure. And now, they break free. The star is pierced from the inside. At its poles, the jets burst into space, and the gamma-ray burst begins. This is not normal light. This is not the warm glow of a star. This is the most energetic radiation in the universe, released in two narrow beams, moving essentially at the speed of light. Gamma rays are light pushed to its most extreme form. Each photon carries far more energy than visible light, ultraviolet light, or X-rays. They can pass through matter, damage atoms, break molecules, and travel across the universe as messengers from the most violent events nature can produce. And now, from the dying star, they are pouring outward. Two beams, focused, brilliant, terrifying. If one of them were aimed directly at us, the event would not be something we simply observe. It would be something we try to survive. But our observation platform is positioned outside the direct beam. We are far enough to live through the event, and far enough from the polar axis to avoid the full force of the jet. Even so, the instruments react instantly. The first signal does not arrive as visible light. It arrives as gamma rays. Before the star brightens to the eye, before the expanding shell becomes visible, before the full hypernova blooms, the detectors are hit by the burst. Every system wakes at once. Gamma ray sensors spike, X-ray detectors flare, radiation alarms activate, the shielding monitors turn critical. The observatory, quiet only seconds ago, becomes a storm of warning lights and automatic commands. The spacecraft turns slightly, shifting its thickest shielding toward the source. Sensitive instruments retract behind protective layers. High-energy detectors switch to emergency modes. Filters darken. Backup sensors come online. The platform was built for this. But even prepared, the burst is overwhelming. The gamma-ray flux rises so quickly that the data stream becomes almost impossible to process in real time. The computers begin prioritizing. Some detectors reduce sensitivity to avoid saturation. Others record only partial slices of the event. Nothing can watch everything perfectly because the universe has just produced more violence than any machine was ever meant to calmly receive. And still, the observatory records. Because this is why we came. The burst lasts 40 seconds. 40 seconds. That sounds short. Less than a minute. A brief flash. A moment. But in cosmic terms, those 40 seconds are enormous. This is a long gamma ray burst, the kind associated with the collapse of a massive star. Some bursts last only milliseconds, some last minutes, but this one holds for 40 seconds, the jet continuing to fire from the heart of the dying star like a cosmic engine refusing to stop. For 40 seconds, the star speaks in gamma rays, and during those 40 seconds, the energy released is almost beyond comparison. A gamma ray burst can release in moments a quantity of energy comparable to what the sun will produce across its entire lifetime, though focused into narrow beams rather than spread evenly in every direction. That focus is what makes it so terrifying. The explosion is not only powerful, it is aimed. A supernova throws energy broadly into space. A gamma ray burst concentrates a portion of the collapse into jets, turning stellar death into a cosmic searchlight. If a planet were directly in the path of this beam, even from great distances, its atmosphere could be changed. The gamma rays would slam into upper layers of air, breaking molecules, creating chemical reactions, stripping away protective compounds, and exposing the surface to dangerous radiation. For a living world, a nearby gamma ray burst aimed in the wrong direction will be catastrophic. At 100 light years inside the beam, survival would not be a realistic word. But outside the direct path, the event becomes observable, still dangerous, still overwhelming, but not fatal. The gamma rays strike the observatory's shielding and scatter through its protective materials. Some are absorbed, some create secondary particles, some produce flashes inside the detectors. The hull vibrates faintly from automatic adjustments, not from sound, but from systems responding to radiation pressure, heat load, and particle impacts. Inside the shielded core of the platform, the viewing systems are no longer showing a simple star. They are showing a data storm, a rising spike, a burst profile, energy changing by the second. The gamma ray signal is not perfectly smooth. It flickers, pulses, rises, falls, then surges again. The jet is not a clean beam from a machine. It is born from chaos, from accreting matter, magnetic fields, rotation, collapse, and the violent central engine of a dying star. The signal carries that chaos. Each pulse is a clue. Each fluctuation tells us something about the engine inside, how fast it spins, how matter falls inward, how magnetic fields twist, how the jet punches through the remaining stellar material. This is no longer only a star dying. This is the universe exposing the physics of collapse in real time. The visible surface has still not fully caught up. That is what makes the moment so strange. The gamma ray burst has reached us. The star has already been pierced. The core has already become something new. But the full visible explosion has not yet unfolded. The opening act is invisible to ordinary eyes. If you look toward the star without instruments, you might see only the beginning of a change, a brightening that has not yet reached its full power. But in high-energy light, the event is already one of the most violent things ever witnessed. The observatory moves into maximum shielding posture. Panels rotate, radiators adjust, data cores isolate. The safest section of the platform turns away from direct exposure while exterior instruments continue taking measurements. Some sensors are sacrificial by design. They may be damaged, even from this distance, but their data is worth the loss. The gamma ray burst continues. 10 seconds. 15. 20. The jet remains active. The beam is not pointed directly at us, but its surrounding radiation environment is still intense. High-energy particles and scattered photons flood the region. The platform's alarms remain active. Radiation levels outside the main shielding are critical. 30 seconds. The burst pulses again. For a moment, the gamma-ray output spikes so sharply that several instruments overload and shut themselves down. Backup arrays take over. The data is incomplete in places, but the overall event is still being captured. 35 seconds. The central engine begins to weaken. Or perhaps the jet direction shifts slightly. Or perhaps the fuel falling into the core begins to change. The signal flickers. 40 seconds. Then the gamma-ray burst fades. Not slowly, not like a sunset. It drops. The first great scream of the hypernova ends, and the silence after it feels impossible. For 40 seconds, the universe produced an event that could be detected across billions of light years. A flash so bright in gamma rays that, if viewed from across the cosmos, it would announce the death of this massive star long before the visible supernova was understood. And now, the burst is gone. But the star is not finished. The gamma-ray burst was only the opening act. The jets have escaped. The core has collapsed. The shockwave is still moving. The outer layers are now being torn apart. Behind the fading gamma-ray signal, the full hypernova is rising. Visible light begins to increase. X-rays continue pouring outward. Ultraviolet radiation grows. The expanding debris, heated by the shockwave and powered by the central engine, begins to shine across the spectrum. The star is breaking open. The gamma-ray burst was the first announcement. Now the universe will see the explosion itself. From our observation platform, systems begin recovering from the burst. Some detectors remain offline. Others continue recording. The shielding stays locked. The radiation outside is still severe, but the worst of the focused gamma-ray phase has passed. The data is beyond priceless. We have recorded the birth of a long gamma-ray burst from close range. We have watched the jets break through the star. We have seen the first signal from the most extreme stellar death. And we have survived because we were not in the beam. That single fact hangs over everything. A tiny change in viewing angle would have turned the event from science into annihilation. That is the nature of gamma-ray bursts. From far away, they are beautiful flashes in telescope data. From the wrong place, they are cosmic weapons. The dying star has now become something far greater than a star. Its core is an engine. Its jets are fading. Its outer layers are exploding. Its light is rising. Its death has already crossed space ahead of the visible blast. And somewhere, perhaps billions of years from now, other observers in distant galaxies may detect this same event as a brief flash of gamma rays in their sky. They will see only the signal, a burst lasting 40 seconds, a line in data, a mystery from deep space. They will not see what we see. They will not know the star's surface, the nebula around it, the jets breaking free, the observatory shields turning toward the blast. They will only know that somewhere far away, a massive star died violently enough to send a message across the universe. From our platform, the main screens brighten again. The gamma-ray burst has ended, but now the star itself is beginning to bloom. The hypernova is coming into visible light. The opening act is over. The real explosion is about to begin. The visible light arrives after the gamma ray scream. For 40 seconds, the star announced its death in radiation, too energetic for human eyes to see. The instruments felt it first. The shields took the impact, the detectors filled with impossible numbers. But now, the universe shows the explosion in light, visible light, the kind of light that can cross space and become an image. The kind of light that, from a safe distance, turns catastrophe into beauty. At first, the star brightens like a point, a single point in the dark. Then that point becomes unbearable. It rises in brightness so quickly that the sky around it seems to change instantly. Where there had been a massive dying star, there is now something far greater, a new light, born from the destruction of the old one. It looks like a new star has appeared, but it is not being born, it is dying. Within seconds, the object becomes the brightest thing in our sky, brighter than any ordinary star, brighter than the surrounding nebulae, brighter than every quiet galaxy in the background. The observation platform darkens its filters again. The visible light telescopes reduce their sensitivity. The cameras shift into protected modes. Even from 100 light years away, the flash is overwhelming. The hypernova is becoming visible. 1 billion suns seem to be concentrated into one point, not spread gently across a galaxy, not softened by distance into a faint glow, but focused into a single violent place where a massive star has just failed from the inside out. The brightness keeps increasing, minute by minute, hour by hour. The gamma ray burst was sudden and brief, but the visible explosion grows like a cosmic fire opening outward. The outer layers of the star are now racing into space. The shockwave has broken through. The star's body is being thrown apart, and all of that heated material begins to shine. At first, the color is almost pure white, blinding, too bright to look at without instruments. Then, as the explosion expands and different layers become visible, the color begins to shift. Blue-white light dominates the hottest regions. Then warmer yellow and gold tones begin to appear. Later, as the gas cools and spreads, deeper oranges and reds will emerge. The hypernova is no longer a point. It is becoming a shape. A shell of material begins to appear around the central brightness. At first, it is only a faint edge, a halo, then a ring, then an expanding sphere of light, racing outward at nearly 30,000 kilometers per second, 1/10 the speed of light. The number does not feel real. Nothing that large should move that fast. And yet the star's outer layers are doing exactly that, blasted outward by the energy of collapse, magnetar rotation, jets, shock waves, and the final death of the core. The shell grows. Every second, it expands by tens of thousands of kilometers. Every minute, it becomes millions of kilometers wider. The star is no longer holding its material. It is becoming a cloud, a nebula in its first violent moments, a cosmic wound opening in real time. From our observation platform, the shockwave becomes visible as a glowing front moving outward from the center. It is not perfectly smooth. It ripples, it bends, it tears through uneven layers of gas. Some regions move faster, some parts are denser, some fragments are launched like glowing islands of stellar matter. The hypernova is not a clean explosion. It is chaos given light. Around the star, old gas clouds suddenly ignite. The star had been shedding mass before it died, Stellar winds had created shells around it. Plasma eruptions had thrown material outward. Those old layers were waiting in space, invisible or faint. Now the hypernova light reaches them. They glow. A light echo begins. The explosion illuminates the surrounding material from the inside out, like lightning revealing clouds in a midnight sky. Arcs of gas appear. Dusty structures brighten. Shells that were thrown away years or centuries before the final death now become visible, lit by the blast that followed them. It is as if the star's past is being revealed by its death. Every layer it lost before the end becomes part of the spectacle. The surrounding nebula glows blue, white, violet, and gold. Shocked gas shines along thin ridges. Dust reflects the explosion light. Radiation ionizes atoms and makes them glow in different colors. The observatory captures it across every wavelength. In visible light, we see beauty. In ultraviolet, we see heat. In X-rays, we see violence. In infrared, we see dust warming. In radio waves, we begin to see particles accelerated by the shockwave. Every kind of light tells a different part of the story. But the most profound part of the explosion is invisible to the eye. Inside the expanding fireball, elements are being created and scattered. The massive star had already forged many elements during its life. It built oxygen, carbon, silicon, iron, and more inside its burning layers. But the hypernova adds the final violence. The extreme temperatures, densities, neutron-rich conditions, and explosive shock allow some of the heaviest elements to form or be thrown into space. Gold, platinum, uranium, elements too heavy and rare to be made easily in ordinary stars. The material that will one day become planets, metals, rocks, oceans, and perhaps life is being launched into the galaxy. Every heavy atom has a history. Some were made in dying massive stars, some in neutron star collisions, some in the most violent stellar environments the universe can create. But all of them require catastrophe. There is no gentle road to gold, no quiet path to uranium. The rarest materials in the universe are born in violence, and now we are watching that violence become creation. The hypernova is destroying everything near it, but it is also enriching space. It is taking the deep interior of a massive star and spreading it outward for future worlds to use. This is why the explosion is beautiful in the most terrible way. It is death becoming chemistry. The shockwave continues outward. Nearby gas clouds are swept up and compressed. Some are shredded apart. Others are squeezed so tightly that millions of years from now, they may collapse into new stars. The hypernova is clearing space and planting seeds at the same time. But close to the blast, there is no mercy. Any planetary system near the star is devastated. Worlds within the inner danger zone are flooded with radiation. Atmospheres are stripped or chemically broken. Surfaces are sterilized. Ice vaporizes. Oceans boil away if they are close enough. Magnetospheres are overwhelmed. The sky itself becomes poison. And for planets caught in the direct path of the gamma-ray jet, the danger reaches much farther. A gamma-ray burst aimed directly at a world across thousands of light years could damage its upper atmosphere, destroy protective ozone layers, and expose the surface to dangerous radiation. It may not tear every atmosphere away instantly, but it could change a living planet's future in a single cosmic event. That is what makes hypernovas terrifying. They do not only kill nearby worlds, Their beams can reach across interstellar distances. A star dies in one place, and planets far away may suffer the consequences. From our platform, we are outside the beam. We are protected by distance and angle. But even here, the radiation remains severe. The shields stay locked. The exterior sensors continue absorbing punishment. Some instruments are damaged, but the main observatory survives. The visible explosion grows brighter still. At peak luminosity, the hypernova becomes far more powerful than an ordinary supernova. It shines with a brilliance that makes the surrounding universe seem dim. For a time, it is the dominant light in this entire region of space. A star that lived for only a few million years now spends its final energy in a display that could be seen across the cosmos. The central region is still too bright to see clearly. The jets have faded, but their scars remain. The explosion is stretched along the star's rotation axis, not perfectly round. Material has been thrown farther in some directions than others. The shape of the future remnant is already being decided. The hypernova is sculpting its own ghost. The shell expands, the shockwave grows, the light echo spreads through the surrounding gas. The first filaments of the future nebula begin forming in the blast, and at the center, hidden behind all that brightness, something dark may already exist. A newborn black hole, or a magnetar spinning so fast that it continues feeding energy into the explosion. The star itself is gone, not faded, not dimmed, gone. Its body has become ejector. Its core has become a compact remnant. Its light has become a cosmic announcement. And we are watching the announcement unfold. For hours, the brightness increases. For days, it remains almost unreal. For weeks, it will dominate the sky. For months, it will fade slowly. But this first visible moment is the most overwhelming. The moment when the hidden collapse becomes visible creation. The moment when the star breaks open. The moment when death becomes light. From the observation platform, the hypernova fills the screens. A blazing white core, blue shock fronts, golden expanding gas, purple and magenta clouds illuminated by the blast. Old shells glowing around it like rings of memory. A star has died, but in dying, it has become more luminous than it ever was in life, and the universe around it will never be the same. The first hours after the hypernova feel strangely different from the first seconds. The opening was violent. A gamma ray burst tearing through space, a visible flash rising so brightly that the star seemed to become the center of the universe. A shock wave breaking through the outer layers. A dying giant turning itself into light. But now, after the first impossible brightness, the event begins to change. It does not become calm. Not yet. Nothing about a hypernova is calm. But the first scream has passed. The gamma ray burst has faded. The most focused beam of radiation is gone. The first blinding rise in visible light has reached its peak and begun the long, slow decline. And now the aftermath begins. From our observation platform, the star is no longer a star. It is an expanding wound, a glowing shell of material racing outward into space, still moving at terrifying speed, still hot, still violent, still bright enough to dominate everything around it. The brightness begins to fade slowly, but only compared to what came before. To human eyes, it would still be overwhelming. A new light in the sky, a cosmic fireball, a point that has become a cloud, a cloud that has become a growing nebula. The expanding material glows in every wavelength. In gamma rays, we see the last traces of the most energetic reactions. In X-rays, we see gas heated to extreme temperatures, shock fronts slamming into older shells of material. In ultraviolet, we see the fierce radiation from freshly exposed, superheated layers. In visible light, we see the beauty, the white, blue, gold, and violet glow of a star's body scattering into space. In infrared, we see dust beginning to warm and form inside the debris. In radio waves, we see particles accelerated by magnetic fields racing through the expanding remnant like invisible lightning. The hypernova is no longer one event. It is many events happening at once. Every wavelength tells a different part of the story. Visible light shows the explosion's face. X-rays reveal its violence. Infrared reveals its cooling ashes. Radio waves reveal its invisible motion. Spectra reveal its chemistry. Neutrinos revealed the death of the core, and gamma rays revealed the birth of the jets. The first hours are when all of those stories overlap. The afterglow of the gamma ray burst continues. The main burst lasted only moments, but the afterglow can last for hours, days, sometimes much longer depending on the environment. As the jet material slams into surrounding gas, it releases energy across the spectrum. The beam that once tore out of the star now leaves behind a fading trace, like a cosmic footprint moving through space. Our instruments follow it carefully. The afterglow weakens, then brightens slightly, then fades again. It is not smooth. The jet is interacting with material the star released before it died. Shells of gas, stellar wind, clumps of matter. All of it changes the way the afterglow behaves. Every flicker is information. Every change in brightness tells us something about the density of the space around the star. The hypernova is lighting up its own history. The material thrown off before the explosion is now being struck by the material thrown out during the explosion. Old layers meet new violence. The star's past collides with its death, and at the center, hidden behind all this light, something remains. A magnetar, or a black hole. If the core formed a magnetar, then deep inside the expanding debris, there is now a city-sized object spinning hundreds of times per second. Its magnetic field is beyond imagination. Its rotation is still pouring energy into the surrounding material. The magnetar becomes a central engine, a heart inside the dead star. It sends energetic particles outward. It drives a wind of electrons and positrons into the debris. It begins carving out a bubble inside the expanding material. This is the beginning of a pulsar wind nebula, not fully formed yet, not beautiful in the way it may become thousands of years from now. But the first signs are there. A central pulse, a stream of particles, a growing region of energized gas around the remnant. The magnetar's wind slams into slower moving debris, heating it and accelerating it. Magnetic fields twist through the cloud. Particles spiral and radiate. The inner region begins to glow with high-energy light. A second nebula is being born inside the first. The outer nebula is the star's body expanding outward. The inner nebula is the compact remnant breathing energy into the ashes. If the center became a black hole instead, the story is darker. Some of the material thrown outward does not escape completely. It falls back. It spirals inward. It forms a disk around the newborn black hole. Before disappearing, the gas heats to extreme temperatures and releases powerful radiation. The black hole itself remains invisible, but the matter dying around it reveals its presence. In that version, the center is not a pulsing lighthouse. It is an absence surrounded by fire. Either way, the original star is gone. What remains is stranger, smaller, denser, and more extreme than the star ever was. Around it, the hypernova continues expanding. The shell is now huge and growing larger every second. Its outer edge is still racing outward. The shockwave sweeps through nearby gas, heating it, compressing it, and making it glow. The first filaments begin to form where the material is uneven. Some regions are rich in oxygen, some in carbon, some in silicon, some in iron. Some contain traces of heavier elements, born or scattered in the violent conditions of the explosion. Our spectrometers begin mapping the chemical structure of the remnant. This is one of the most important parts of the observation, because a hypernova is not only a blast of light, it is a chemical event. The star spent its life forging elements in its core. The hypernova throws them into space. The explosion mixes them, heats them, reveals them, and sends them outward into the galaxy. Oxygen appears in abundance. Carbon is there. Silicon, calcium, iron, nickel. The fingerprints of stellar burning are written across the light. Then come the rare elements: silver, gold, platinum, uranium. Not every atom of these elements in the universe comes from exactly the same kind of explosion. Some are made in neutron star collisions, some in rare explosive environments, some in the deaths of massive stars under extreme conditions. But here, in the violence of this hypernova, the ingredients of future worlds are being released in extraordinary quantity. The universe has just become richer, not metaphorically, literally. Space now contains more heavy elements than it did before the star died. Matter that had been locked inside the core is now free. Matter that could never become planets, while trapped inside the star, is now spreading outward. The observatory creates a map of abundance, where oxygen is strongest, where silicon dominates, where iron-rich material expands, where heavier elements appear in the debris. It is like watching the periodic table being scattered into the dark. Every color in the spectrum is a clue. Every absorption line, every emission line, every shift caused by the speed of the expanding gas. The hypernova is writing its chemical autobiography in light, and we are reading it as it happens. The first hours are also when the true shape of the explosion begins to reveal itself. It is not a perfect sphere. The jets made sure of that. The rotation of the core shaped the blast. The magnetic fields directed energy. The star's uneven outer layers changed how the shock wave escaped. The remnant is stretched along one axis. Some material moves faster in the direction of the jets. Other material expands more slowly around the equator. From a distance, the explosion begins to look like a cosmic flower opening unevenly. A bright center, two extended lobes, a glowing shell, filaments reaching outward, purple and blue high-energy regions, gold and red cooler gas, white-hot knots where the shock wave strikes dense material. It is beautiful now, still deadly, still saturated with radiation, still dangerous to any nearby world, but beautiful. And that beauty is almost difficult to accept because we know what it means. A star has died. Any planets close to it are gone as habitable worlds. Any fragile life nearby would have been erased. But the same event that destroys its neighborhood is now seeding the wider galaxy. The heavy elements expanding outward may one day enter a molecular cloud. That cloud may collapse. A new star may ignite. Dust may gather around it. Planets may form. Some of those planets may contain iron from this explosion, silicon from this explosion, oxygen from this explosion, maybe gold from this explosion, maybe uranium from this explosion, maybe carbon that becomes chemistry, maybe chemistry that becomes life. That is the impossible dual nature of a hypernova. It is death at close range, creation at cosmic range. From our platform, the first hours continue. The central brightness fades slightly more. The afterglow weakens. The expanding shell becomes clearer. The spectroscopic maps grow richer. The shockwave continues its outward march. The star's body is becoming part of interstellar space, and the instruments keep recording. They capture data no civilization could ever recreate in a laboratory. No machine could compress a star. No experiment could build a magnetar. No human technology could produce a gamma-ray burst. We can only watch, and from watching, understand a little more. The hypernova is still young, only hours old. Its light will fade over weeks and months. Its remnant will glow for thousands of years. Its material will travel for millions. Its atoms may survive for billions. And one day, long after the explosion is forgotten, those atoms may become part of something quiet, a stone, an ocean, a living cell, a breath. The first hours after a hypernova are not the end. They are the beginning of the aftermath. The star is gone, but its matter has entered the universe again. The darkness around it is full of new elements, new motion, new light, new possibility. A giant star has died, and the universe has become richer because of it. Days after the hypernova, the sky has still not returned to normal. The first flash is gone. The gamma-ray burst has faded. The most violent opening seconds have passed. But the explosion is still there, still bright, still expanding, still changing the space around it. From our observation platform, the dying star no longer looks like a point. It has become a growing structure, a brilliant center surrounded by an expanding shell of glowing material. The brightness has begun to fall, but only compared to the impossible peak that came before. To anything watching from a nearby system, it would still look like a new star had appeared in the sky, a star that was not there before, a star brighter than anything else, a star born from death. For days, the hypernova continues to dominate its region of space. Its light floods surrounding dust and gas. Its expanding debris glows across every wavelength. The central brightness slowly weakens, but the remnant becomes more beautiful as the details emerge. At first, the explosion was too bright to understand. A white-blue fireball, a single overwhelming source of light. But now, as the outer layers race outward and cool, the shape begins to reveal itself. The expanding nebula becomes larger, more structured, more complex. Filaments begin to appear. Thin glowing threads of gas stretch outward from the center. Dense knots form where material clumps together. Some regions move faster, others lag behind. Some parts are shaped by the old stellar wind that surrounded the star before it died. Other parts are shaped by the jets that tore through the star during the collapse. The remnant is not a perfect sphere. It is scarred by the way the star died, the rotation of the core, the direction of the jets, the uneven layers of the star, the shells of gas thrown off before the explosion. All of these things are now written into the shape of the nebula. The hypernova is becoming a cosmic fingerprint. And then the colors begin to separate. Different elements cool and glow in different ways. Hydrogen shines in red. Oxygen glows in green and blue-green. Sulfur adds orange and deep red tones. Iron-rich regions appear in hotter, higher energy light, glowing in blue-white and X-ray colors through our instruments. To the eye, the remnant would be beautiful. But through the full range of our observatory, it is almost beyond beauty. It is a map of chemistry, a glowing periodic table expanding into the dark, red streams of hydrogen, green oxygen shells, orange sulfur knots, blue-white high-energy regions, purple shock fronts, gold dust scattering the dying light. The most colorful object in the sky is not a living star. It is the remains of one. That is the strange truth of stellar death. A star can become more visually beautiful after it has been destroyed than it ever was while it lived. When it was alive, it was a sphere of light. Now it is a structure, a nebula, a wound, a flower of gas opening in space. Days pass. The brightness continues fading, but the nebula grows. The shell expands farther from the center, moving at thousands and thousands of kilometers per second. The shockwave pushes into the material surrounding the star. It strikes older gas clouds, compresses them, heats them, and makes them shine. Where the shockwave hits dense material, bright arcs appear. Where it passes through thinner regions, the gas stretches into faint veils. Where heavy elements are concentrated, the spectrum changes. The observatory records everything, every color, every line, every motion, every shift in brightness. We are no longer watching only an explosion. We are watching the birth of a supernova remnant, a structure that may remain visible for thousands of years. Weeks after the hypernova, the first overwhelming glare has faded significantly. The center is no longer the only thing we can see. The remnant now has shape, depth, and texture. It looks like a vast, luminous shell. But inside that shell are smaller structures, ribbons, knots, bubbles, shocked clouds, twisted streams of plasma. Some filaments glow like burning threads. Others look soft and ghost-like, drifting into the surrounding darkness. The whole structure continues expanding, but not evenly. It grows like something alive, though it is only physics, pressure, heat, and motion. And then the shockwave reaches the nearby gas clouds. These clouds were not part of the star itself. They were already there in the surrounding region. Cold gas, dust, and molecular material drifting through space. Before the hypernova, they may have been quiet, dark, waiting. Now the shockwave slams into them. The gas compresses, the temperature rises, the cloud surfaces light up. For some parts of the cloud, the blast is destructive. It tears material apart and pushes it away. But in other regions, the compression may do something extraordinary. It may help create new stars. When gas clouds are squeezed hard enough, gravity can take over. Dense pockets can collapse inward. Over long timescales, those pockets may become protostars. Around them, disks of dust may form. Inside those disks, planets may eventually grow. This is one of the deepest paradoxes in the universe. The hypernova destroys everything close to it, but farther away, it may help create the next generation. Death and creation are happening at the same time. Near the blast, planets are sterilized, atmospheres are damaged, moons are burned, orbits are disturbed. But farther out, cold gas is being compressed into future stars. The same shockwave that kills one system may help start another. The same explosion that ended one star may light the fuse for thousands more. And the material carried by the blast is rich. The star has released oxygen, carbon, silicon, sulfur, calcium, iron, nickel, and heavier elements into the surrounding space. Some of those atoms will drift for millions of years. Some will mix into molecular clouds. Some will become part of stars that do not yet exist. Some will become planets. Some may become oceans. Some may become life. The galaxy is permanently changed by this single event. Before the hypernova, this region of space had one massive star nearing death. Now it has a glowing remnant, an expanding shockwave, enriched gas, heated dust, compressed clouds, and perhaps the beginning of future star formation. One star is gone, but the region around it is more complex than before, richer, more energetic, more chemically alive. At the center, the compact remnant continues its work. If a magnetar formed, it is still spinning, still pulsing, still pouring energy into the nebula. Its rotation is gradually slowing as it loses energy, but that energy does not vanish. It flows into the surrounding debris. It accelerates particles. It twists magnetic fields. It lights the inner regions of the remnant from within. A pulsar wind nebula begins to grow. At first, it is hidden inside the larger shell, but our X-ray and radio instruments can see it. A bubble of high-energy particles forms around the magnetar. It pushes against the expanding debris, carving a glowing cavity inside the remnant. The magnetar is like a heart inside the dead star, a tiny spinning engine surrounded by the star's scattered body. Pulse after pulse, rotation after rotation. Energy streams outward. The nebula responds. It glows. It shifts. It lives on borrowed power from the dead core. And it may continue doing this for thousands of years. Long after the hypernova's visible light fades from ordinary sight, the remnant will remain. The shockwave will keep expanding. The magnetar, if it survives, will keep feeding the inner nebula. The gas will keep cooling, glowing, and mixing with the galaxy. Future astronomers, thousands of years from now, might look toward this region and see a beautiful nebula. They might not witness the explosion. They might never know what it looked like when the sky first changed. But they will see the aftermath. They will see filaments. They will see glowing oxygen. They will see shocked gas. They will see the shape carved by jets. They will see the chemical remains of a hypernova. And if they understand what they are looking at, they will know that a massive star died there. A rare star, a powerful star, a star whose death was violent enough to alter an entire region of space. From our platform, weeks after the blast, the sight is no longer pure terror. It has become something quieter, still enormous, still dangerous, still filled with radiation and motion. But now, beauty begins to dominate. The nebula spreads across the darkness like a cosmic painting. The colors deepen as the gas cools. The shockwave lights up distant clouds. The central magnetar pulses through the debris. The first outlines of the future remnant are clear, and the star itself is nowhere to be seen. Its surface is gone. Its core is transformed. Its outer layers are now space. The star has become a cloud of elements, a wave of energy, and a seedbed for the future. That is the aftermath of a hypernova. Not silence, not emptiness, not a clean ending, but a spreading consequence. For days, it blinds the sky. For weeks, it becomes a nebula. For thousands of years, it glows as a remnant. For millions of years, its shockwave travels. For billions of years, its atoms continue. One star's death enriches an entire region of space. One collapse creates light that can cross the universe. One explosion scatters the ingredients of worlds that have not yet formed. And as we watch the glowing shell expand, we understand the strange law written into the stars. The universe does not waste its endings, it turns them into beginnings. The terrifying question is simple. Could one of these happen near Earth? Could a massive star somewhere in our galaxy collapse into a hypernova, launch a gamma-ray burst, and send one of those beams directly toward us? The answer is uncomfortable. Yes, in principle, it could happen. But the full truth is more complicated and far less immediate than the fear sounds. A hypernova is dangerous because it is not only an explosion, it is an explosion with direction. The visible blast expands outward in many directions, but the gamma-ray burst, if one forms, escapes as narrow jets from the poles of the dying star. That means location matters, distance matters, but direction matters most. A hypernova could happen somewhere in the Milky Way and be spectacular but harmless to Earth if its jet points away from us. But if the star is close enough, and if the beam points directly toward Earth, then the danger becomes planetary. The radiation would not burn the ground directly like a fire. It would not arrive as a visible wall. It would not make the oceans instantly boil. The greatest danger would begin high above us in the atmosphere. Gamma rays from a nearby burst would strike the upper atmosphere and trigger chemical reactions. Nitrogen and oxygen molecules would be broken apart and rearranged. Compounds would form that could destroy ozone. And the ozone layer is one of Earth's quiet shields. It protects life from dangerous ultraviolet radiation from the sun. If a gamma-ray burst damaged that layer badly enough, sunlight itself would become more dangerous. Ultraviolet radiation would reach the surface in higher amounts. Plankton in the oceans could be harmed. Food chains could collapse from the bottom upward. Land life would face increased radiation stress. Climate chemistry could shift. The danger would not be a single flash killing everything at once. It would be the after effect. The sky changed chemically. The planet's protection weakened. The sun becoming more dangerous because a star far away died in the wrong direction. Some estimates suggest that a gamma-ray burst within several thousand light-years, if aimed directly at Earth, could cause severe biological and atmospheric damage. A distance around 8,000 light-years is sometimes discussed as a rough danger zone for powerful bursts, but the exact risk depends on the energy of the event, the angle of the beam, the duration of the burst, and the condition of Earth's atmosphere at the time. So the threat is not simply distance, it is alignment. A hypernova must be close enough, powerful enough, and aimed at us. That combination is rare, but over deep time, rare events become possible. Some scientists have wondered whether a gamma-ray burst could have contributed to one of Earth's ancient mass extinctions, especially the Ordovician extinction about 450 million years ago. During that event, a large fraction of marine life disappeared. The cause is still debated, and the leading explanations involve climate change, glaciation, sea level change, and ocean chemistry. But a gamma-ray burst has been proposed as a possible trigger or contributing factor because it could damage the ozone layer and affect life near the ocean surface. The evidence is not conclusive. There is no crater, no direct fossil labels saying a gamma-ray burst happened, no simple proof. But the idea remains haunting because the pattern is physically possible. A burst could leave no obvious impact scar, yet still change atmospheric chemistry enough to stress the biosphere. A star could die thousands of light years away, and Earth could suffer without ever being touched by debris. That is what makes gamma-ray bursts so different from asteroids. An asteroid leaves a wound. A gamma-ray burst leaves a chemical ghost. So we look around the galaxy and ask, are there stars nearby that could become hypernovas? One of the most famous names is WR104. WR104 is a Wolf-Rayet star system, roughly thousands of light years away, often discussed because of its beautiful spiral dust pattern. That spiral suggests a binary system with powerful stellar winds shaping dust into a rotating pinwheel. For years, WR104 attracted attention because some early interpretations suggested its rotation axis might be pointed roughly toward Earth. If a long gamma-ray burst were produced along that axis, and if Earth were inside the beam, then WR104 became a frightening candidate in popular science discussions. But later studies made the situation less certain and less terrifying. The geometry is difficult. The exact angle matters enormously. Many astronomers do not consider WR104 an immediate danger. Even if it does eventually explode, there is no guarantee it will produce a gamma-ray burst, and no guarantee any beam would point at us. Still, it remains a star we watch, not because panic is useful, but because massive stars near the end of life are important. Another famous object is Eta Carinae. Eta Carinae is one of the most extreme stellar systems in our galaxy. In the 1800s, it underwent a massive eruption known as the Great Eruption, becoming one of the brightest stars in the sky for a time. It did not die then. It survived. But the eruption showed how unstable extremely massive stars can become. Eta Carinae may one day explode as a supernova, or perhaps something even more powerful, depending on its final state. But again, danger depends on distance and direction. Eta Carinae is thousands of light years away, and its likely dangerous axis does not appear to be aimed directly at Earth in the way required for the worst-case gamma-ray burst scenario. So it is not a reason for fear tonight. It is a reason for study. Across the galaxy, astronomers monitor Wolf-Rayet stars, luminous blue variables, massive binary systems, and other unstable giants. They study their winds, rotation, mass loss, spectra, magnetic fields, and surrounding nebulae. They are searching for clues. Which stars are close to collapse? Which ones are massive enough? Which ones are rotating fast enough? Which ones have lost their outer hydrogen layers? Which ones might create jets? Which ones might become neutron stars, magnetars, or black holes? Modern sky surveys watch the night repeatedly. Space telescopes monitor high-energy events. Gamma-ray observatories detect bursts from across the universe. Neutrino detectors wait for the first invisible warning of a nearby collapse. Gravitational wave observatories listen for the most violent motions of compact objects. If a massive star in our galaxy were about to die, we might not know the exact hour. But when the core collapses, the universe would send warnings. Neutrinos first, then high-energy radiation, then light, then the expanding remnant. The honest probability of a dangerous hypernova affecting Earth during a human lifetime is extremely low. Not zero, but extremely low. The galaxy is vast. Hypernovas are rare. The beam is narrow. The alignment must be precise. And human lifetimes are very short compared to cosmic time. But over millions of years, the story changes. Given enough time, massive stars will continue to die. Some will become supernovas. A smaller number may become hypernovas. Some gamma-ray bursts will be aimed somewhere. Some planets may lie in the wrong direction. The universe is violent on timescales we cannot easily comprehend. Earth feels safe because our lives are short. The sky feels calm because we see only a tiny moment of cosmic history. But the galaxy is full of processes that unfold across millions and billions of years. Stars are being born, stars are dying, black holes are forming, neutron stars are merging, shockwaves are moving through ancient gas clouds. Somewhere right now, a massive star may already have collapsed. Somewhere, a jet may already be crossing interstellar space. Somewhere, a hypernova may have happened thousands or millions of years ago, and its light has not reached us yet. That is one of the strangest truths in astronomy. The universe can already contain an event before we know it happened. A star may have died. A gamma-ray burst may have been launched. A wave of radiation may be crossing the darkness. And for us, the sky remains unchanged because the light is still on its way. If a hypernova happened 10,000 light years away, we would not see it for 10,000 years. The event would already be history at its source, but still future for Earth. The universe is full of delayed truths. Deaths that have happened but not arrived. Explosions already finished but not yet visible. Messages crossing space at the speed of light, waiting for the moment they enter our sky. That is why a hypernova near Earth is terrifying, not because it is likely tomorrow, but because it reminds us that our planet lives inside a galaxy that is not quiet. Earth is protected by distance, by atmosphere, by magnetic field, by luck, by the fact that most cosmic violence happens far away and points elsewhere. But we are not separate from the galaxy. We live inside it. The stars around us are not decorations. They are engines. Some are ancient, some are young, some are stable, some are already unstable. Some will die gently, some will explode. A rare few may die as hypernovas. And all we can do is watch, measure, understand, prepare our instruments, and remember how precious our calm sky really is. Because somewhere tonight, in a galaxy far away, or perhaps in our own Milky Way, a massive star is approaching its final moment. Its core is building iron. Its surface still shines. Its surrounding gas glows softly in the dark. The collapse has not yet reached the light, but it will, and when it does, the star may announce its death with one of the most powerful flashes the universe can create. A hypernova, a beam of gamma rays, a new light in the sky, a reminder that the universe is beautiful because it is dangerous. There is a strange truth hidden inside every hypernova. It looks like destruction, It feels like the universe losing control. A massive star collapses. Its core breaks. Jets tear through its body. Gamma rays flash across space. The outer layers explode outward with enough energy to reshape everything nearby. From close range, a hypernova is death. It sterilizes worlds. It destroys atmospheres. It tears apart planetary systems. It floods space with radiation. It leaves behind a neutron star, a magnetar, or a black hole where a giant star once lived. And yet, without events like this, the universe would be far less alive, because hypernovas do something ordinary stars cannot do easily. They take the deepest material inside massive stars and throw it into space. They scatter heavy elements across the galaxy. They enrich cold gas clouds with the ingredients that future planets will need. And in that way, the most violent deaths in the universe help make life possible. A young universe was simple. Mostly hydrogen, mostly helium, a little lithium. Beautiful, but chemically poor. There were no rocky planets at first, no oceans, no iron cores, no mountains, no oxygen-rich air, no DNA, no bones, no blood, no life as we understand it. The first stars had to live and die before the universe could become complex. Inside stars, lighter elements are fused into heavier ones. Hydrogen becomes helium. Helium becomes carbon and oxygen. Massive stars go further, building neon, magnesium, silicon, sulfur, calcium, and iron. But many of the rarest and heaviest elements need something more violent. They need extreme heat, extreme pressure, extreme neutron-rich environments. They need stellar death, supernovas, hypernovas, neutron star mergers, and other violent cosmic events create and scatter the elements that ordinary stars cannot quietly produce. The gold in jewelry, the platinum in machines, the uranium in nuclear reactors, the rare elements hidden inside Earth's crust. They all carry a memory of cosmic violence. Not every atom comes from one kind of explosion. The universe has many factories. Some heavy elements are forged in neutron star collisions, some in supernovae, some in the extreme deaths of massive stars. But the truth remains the same. The rarest materials in our world were not made gently. They were born in catastrophe. A hypernova is one of the universe's most dramatic ways of turning a star into future chemistry. The dying star does not simply vanish. It opens. It releases carbon, oxygen, silicon, iron, and heavier elements into space. It pushes them outward in a shockwave. It mixes them into the surrounding interstellar gas. It spreads them across a region that may one day become a nursery for new stars. And then, over millions of years, gravity begins again. A cloud enriched by the hypernova slowly cools. It gathers. It collapses. A new star forms at the center. Around that star, dust collects into a disk. Inside that disk, tiny grains collide. They stick. They grow. They become rocks, then planetesimals, then worlds. Some of those worlds may have iron cores because ancient stars died. Some may have rocky crusts because explosions scattered silicon and oxygen. Some may have radioactive elements inside them, warming their interiors for billions of years. Some may have carbon chemistry. Some may have water. And if the conditions are right, some may have life. That is the profound connection. A hypernova can destroy nearby life. But far away and far in the future, it may help create the ingredients for life somewhere else. The same event that ends one star can become the beginning of thousands of worlds. This is why the universe is so strange. Creation does not always look gentle. Sometimes creation begins as collapse. Sometimes beauty begins as violence. Sometimes the atoms needed for life are made only when something enormous dies. Without heavy elements, there is no complex chemistry. Without complex chemistry, there is no DNA. Without DNA, there is no biology like ours. And without the deaths of ancient stars, there would be no Earth, no oceans, no continents, no plants, no animals, no humans looking up into the night sky, wondering where all of this came from. We are connected to these explosions in a way that feels almost impossible. The iron in the ground, the oxygen in the air, the carbon in your body, the calcium in your bones, the trace elements that help cells function. All of them were once part of a cosmic story much older than Earth. Somewhere, long before the sun existed, stars lived, burned, collapsed, and died. Their remains drifted through space. Their ashes became part of the cloud that formed our solar system. And from that cloud came the sun, the planets, the oceans, and eventually life. That means a hypernova is not just an astronomical event. It is part of the family history of matter, a violent ancestor of worlds, a moment when the universe takes one of its largest stars and recycles it into complexity. The star dies, but the material continues. The explosion fades, but the atoms keep traveling. The remnant cools, but the elements survive. They drift through space for millions or billions of years, waiting for gravity to gather them again. One day, they may become part of a new planet, a mountain, a sea, a living cell, a thinking mind. And perhaps that mind will one day look up and study hypernovas, never realizing that its own body may contain the ashes of events just like them. That is the poetic truth. The most violent events can create the most beautiful outcomes. A hypernova is terrifying because it shows how powerful destruction can be. But it is beautiful because it shows that destruction is not always the end. In the universe, endings are often transformations. A massive star becomes a blast wave becomes a nebula enriches a cloud becomes a star system becomes planets, a planet becomes alive, life becomes aware, and awareness looks back at the stars. Future hypernovas are happening somewhere right now. Maybe not in our part of the galaxy. Maybe not close enough to see with the naked eye. Maybe in a distant galaxy whose light will not reach us for millions of years. But somewhere, a massive star is nearing its final collapse. Its core is changing. Its final fuel is burning. Iron is building. Gravity is waiting. And when the moment comes, it will end in light. The jets will break through. The gamma ray burst will flash. The outer layers will explode. The remnant will expand. And new heavy elements will be thrown into space. Those elements may one day become part of future planets. Not planets that exist now, not worlds with names, but future worlds. Worlds around stars that have not formed yet. Worlds that may orbit peacefully billions of years from now. Worlds with oceans under alien skies. Worlds where chemistry begins in warm pools, deep vents, frozen seas, or strange atmospheres. Worlds where life may appear because a massive star died long before they were born. That is what hypernovas mean for life. They are not only disasters, they are cosmic seeders. They scatter the materials that make the universe richer than it was before. They turn giant stars into the dust of future worlds, and they remind us that life does not emerge from a peaceful universe alone. Life emerges from a universe that changes, a universe that burns, a universe that collapses, a universe that destroys and rebuilds again and again. Tonight, as you drift to sleep, somewhere in the galaxy, a massive star may be living its last moments. Its core is changing, its final elements are forming, its iron is building, and soon, in cosmic terms, it will end. Not quietly, not gently, but in a flash of light brighter than billions of suns. And in that violence, the seeds of something new will be scattered across the cosmos. Perhaps the seeds of a world like ours. Perhaps the seeds of oceans not yet formed. Perhaps the seeds of life not yet born. The universe destroys to create. It breaks stars open so future worlds can exist. It turns death into chemistry, chemistry into planets, planets into life, and life into wonder. So sleep now beneath the quiet light of our own star, and remember that somewhere, far away, another star is preparing to give itself back to the dark, not as an ending only, but as the beginning of something new.